Okay, so we're going to talk a few moments about some of the things Mr. Donnan brought up. Um, One was this term chromatic aberration, and what that is when you have light that comes to the outer edges of your lens, because the fact that the index of refraction for light is different at different wavelengths. If you have different colors coming in, so say this is red, and this is, that's, I'm not sure which way it bends more so, but what'll happen is instead of the ray going through as white, the different colors will get separated, like in a prism. And that happens more outside near the edges. If you remember our experiment where we were rotating the lens and we got close to total internal reflection, you started to see the light separate into the different colors. And so because of that, you would get, your picture would be out of focus, and because the colors would be separated. So I don't know exactly how they do it, but obviously these lenses are not just two convex pieces of glass. There's all kinds of combinations. So that's what chromatic aberration is. And so I guess, I don't know if, I think it's all done optically, not done digitally, to correct those kinds of things. One thing, he mentioned the cover. My cover is not quite as big as his cover. I have cover envy. But you see that one has a little thing that pops out. And this one, the same thing. So these telephoto lenses have a shade. And that's just to, as he was saying, with your cell phone camera, if you can keep your hand over top of it, especially if there's sunlight, because what will happen is the sun will come into your lens, and you really don't want the sun in there. You just want the light from the things you're taking a picture of. So this was he was talking about the 100 millimeter lens. This is a 100 millimeter lens. This one is a zoom lens. So, in this case, you just focus it by changing the focal length of the lenses. Here, this causes it to zoom, and this causes it to focus. So the zoom is this direction, and you can actually, on the side of the lens, this is 80, this is 200. So this is an 80 millimeter. So this lens in this configuration has less zoom than this one does. But if you pull that down to here, it's a 200 zoom versus 100 zoom, so it has twice the amount of zoom on it. So if you look through this with the camera, you'd be like a telescopic thing this way, and then once you got to a point that you had the image the size that you wanted it, then you could adjust the focus on the thing. And another thing that comes with these cameras is this, which is your Polaroid lens. So if you're taking pictures, say over water, and you don't want the glare from the water, you would take this and you would put it onto all these lenses have where's the screw thing here? All these lenses have things that you can screw the Polaroid coated lens in there. So there, I don't know why it's not tightening up completely. Oh, there we go. Yeah, so now it's got the Polaroid. Now normally even this lens that I have on my camera here, it's not a Polaroid, it's just a kind of a protective lens. So there's a cap, and it does something, I forget what exactly it does. It's called a skylight filter. So I think it helps also with just eliminating glare, but not through Polaroid. I don't know what exactly it does, but how it does it. But it also protects the lens of the camera, so you can't touch it accidentally. Okay. He was talking about colors. He said you can create. A computer screen is made up of red, they're RGB displays, red, green, blue. And so you can't create every color, but you can create most colors from those three primary colors. And it all depends upon at what ratios. If you've ever used a desktop publishing program or a camera program, you can adjust the color. You can make it redder, greener, or bluer, and all you're doing is you're just taking the percentage of the different colors and changing the quantity. I guess I'm trying to remember. I mean, I think this even does it if you. Yeah. So you can adjust. I think you can move this around inside this. Well, that doesn't. It's changing the hue and the saturation and the luminosity. But I think and they probably go from 0 to 255. Yeah. So if I put 100 in there for red and 50 for green and maybe 98 for blue. So that's the color it comes out as. Oh, I put 255. No wonder it was so blue. I was like, what happened? 98 for blue. So it's kind of a purplish. And if you fully put in 255 for all of them, you get white. If you put 0 in for all of them, you get black. Like that. Okay, so they're all percentages of these different colors. And so you can create a wide range of different shades. And if I click on this, it'll tell me what it is. So this green is, actually it's 255. That's a lot of green. Let's see. Yeah. So this brownish orange is, so you can see how the numbers change here as I click on the different basic colors. Red, that's 100% red. This one's fully red with about half green and half blue. Now in printing, when you print paper, they don't use the same three colors. So in like computer screens, they use RGB, red, green, blue. In printing, I might have mentioned this before, they use CMYK. CMK, I guess it'd be CMYK, I guess. Usually K's on the end, I forgot. Hold on a second. My thing's making noise. So you have C, which is cyan. You have M, which is magenta. You have Y, which is yellow. And you have K, which is black. You don't use B for black because you use B for blue. And you can create on a printed page, you can create all those different colors that you see on a page using those. And I think it's because one is absorbing the light and then reflecting it. The other one is actually creating the light. I think that's the reason there's a difference there.
Yeah, because if you're absorbing light for all three of CMY, you're going to get black. But if you're emitting light for RGB, you're going to get white, and nobody would want to print that.
Yeah.
So, yeah.
Yeah, you don't want to print white because paper's white. Right, so that's probably, yeah. So let me just show you what those colors look like. I mean, cyan's looks kind of blue. Magenta looks kind of red. So CMYK. So there they are. So cyan, magenta, yellow, black. Now you can't get there's other things called Pantone colors, and those if you are a printer or a graphic designer and you're looking for a specific color, they have this thing called a Pantone. Let me show you this. Pantone colors 2018. Okay. Yeah, so here's you've got all these different kinds of colors. It's like paint swatches. And Hawaiian surf, yeah, that looks good. Citrus. Okay, so you've got all these custom colors, and if you wanted to, you can try to match these colors using CMYK, using the 4 colors, or you can actually just buy the ink that has that particular color exactly. And using 4 color process, you're probably going to get pretty close to it, but if you're really picky about your colors, then you do this Pantone stuff. I don't know if this is like a trade name or whatever it is. Okay, so that's that comment. And then he's talking about the different light. So I think I showed you a picture, but let me find another one here. So if you look up light versus Kelvin or something like that, Kelvin. So depending upon the light source, what daylight is daylight? What is daylight in Kelvin? So the light source, the most natural light source is sunlight, and it depends upon what time of the day it is. But so they've got these ranges for different kinds of light. Soft white, you've probably seen those with light bulbs. They're kind of a yellow tint to them. Then you've got cool white. This is a light bulb, 3500 Kelvin to 4100 Kelvin. Sometimes they actually are bodies that are that temperature, that are radiating. There's probably other ways of getting the same light content without, an LED is not going to be 3000 Kelvin, but you can probably somehow work with LEDs to get an equivalent to a certain Kelvin. And so it's what colors are more prevalent. So if you have daylight, that's going to be high temperature, because the surface of the sun, the interior of the sun is millions of degrees probably Kelvin, but the actual surface of the sun is not that warm. And so the part that we see is the surface, and that's going to be probably 5000 to 6500 Kelvin.
Well, I think the color, the light being emitted is a function of the temperature, but also what's being burned, right?
Well, I think they're connected. I mean, what's being burned. And also depends on, like, the sun. The interior is hotter because it's the energy's trapped in there. So you have nuclear reactions going on, converting hydrogen to helium, and so it reacts and it releases energy, but it doesn't have anywhere to go except outward. It can't go inward. And so as it goes out, it's going to get cooler, because as you get to the surface, it's radiating that energy away. There's no conduction heat transfer or convection heat transfer, because there's no fluid. It's just vacuum. So all that light, all that energy on the outside of the sun is dissipated through radiation or electromagnetic radiation. So yeah, you can characterize the kind of light by the temperature the temperature of the body that emits that kind of light. And daylight's coming from the sun. So I wonder if the question is, how do you get 6000 Kelvin with an LED? Because it's definitely not 6000. Different colors of lighting. LED color temperature differences explained. And what they probably do, you can see here, these are the different temperatures. So yellow, average stock, what's an HID? Does anybody know? Sean, is that something you know? It looks like headlights. Yeah. Something to do with headlights.
So like my headlights in my Xterra are like 6500K,
Oh, you have some of those. Oh, you're one of those guys with the really. Yeah. Yeah, one of those. Yeah, that's right. You got lights that just look different than everybody else's. Is it really? I'll have to. Yeah, I'll have a field trip to Sean's car at night. But yeah. Anyway, so yeah, you can. And what they're doing here, instead of using the temperature, is probably just using different colors, different color LEDs to simulate. Oh yeah. Yeah, that's probably more due to just the energy dissipation because the amount of energy you're putting out, probably not. They're probably not 6,000 K. That would be dangerous. Hmm. Yeah. Mm. Yeah. Still, I think it's more just the amount of power your headlights are just so powerful that even an LED, even though it consumes a lot less power than an incandescent or a halogen or whatever used to be used, it's still, I mean, it still can be significant. If it gets too hot, then you're going to damage things. So
Well, it's funny because I think so the hardest LED, what they struggled with was making blue LEDs
yeah,
because it would be hottest in the spectrum. Right? Yeah, highest in Kelvin. So they had to use indium and gallium.
yeah, but I doubt that's. I think that's just to do with producing that color light, not temperature-wise. It's not a temperature issue. It's just trying to make blue using. I mean, I'm sure red is the easiest thing to make an LED, which I think is probably one of the um, longer wavelengths. I would think. Is that right? Or is it the other way around? Anyway, it's on the other end of the spectrum. Okay, so that's my last comments about light. So what we were doing last time is we were taking 4 kilograms of water and we were increasing the temperature from 15 degrees C to 140 degrees C. And how far did we get? Does anybody take notes last time? Pretty sure we got somewhere in here. So, oh, you lost it. Yeah, I think we were about. I think we did this one. So yeah, so I think we were right here. So to melt the ice, you just take the latent heat of fusion and multiply it by the mass. And the latent heat of fusion was 334,000. So you multiply that by 4 and you get that. Then you increase the temperature from 0 degrees C to 100 degrees C. And because it's one phase, you use Q equals mc delta T. Delta T is 100 degrees C. For water, C is equal to 4,190 joules per kilogram Kelvin. So you take this times 100 times 4 kilograms, and you get 1,676,000 joules. So let me just write it out. I remember doing that. I was like, oh, I didn't write out what was made. I just write the answer. So it's going to be equal to the mass, 4 kilograms, times the specific heat, 4190, times the temperature increase, which is 100, and that gives you that number. Okay, the next thing you do is to boil the water at one temperature, at a fixed temperature. So again, you use this latent heat of vaporization times the mass 4 kilograms. So what we're doing is taking 4 kilograms times 225,600 joules per kilogram, and that gives you that number. And then finally, once it's steam, you can heat it higher than the boiling point. That's called superheated steam. And again, it's one phase. We know it's one phase because if it was phase change, we wouldn't have a temperature change. So we have a temperature change of 40 degrees C, and we have the same mass. And so what you do is you take, so the Q here is going to be 4 kilograms times the specific heat of steam, which is 2,000 joules per kilogram Kelvin times 40 degrees C. And if you multiply those together, you get that number. And then if you add all the numbers together, so if you add the energy required to heat the ice up to freezing, to melt the ice, to heat the water up from 0 degrees C to 100 degrees C, the energy required to boil the water, and the energy to superheat the steam to 140 degrees C, you add all those numbers together, all those 5 numbers, and you get 12,484,000, which this is where it's nice to have prefixes multiplying. So it's 12.5 million, so it's 12.5 megajoules. But a joule is not that much. You know, it's not that much energy. Okay, so that's pretty much all you have to do. I'm sure there's a homework problem that does something like that. I put this on the test. I usually put a problem very similar to this, except I start either as frozen ice and go to liquid water, or liquid water and go to superheated steam. So you don't necessarily have all the steps, but you do have to know when you are at a given phase, you use this result, and if you're changing the phase, you use that. And the last topic in chapter 10 is what are called calorimeters, and you might remember those. They may have discussed those in chemistry, and that's to figure out heats of reaction. In physics, we don't talk about heats of reaction. We talk about figuring out what the specific heat of a substance is. So the whole idea is you have an insulated vessel of some sort, and typically you have some kind of liquid, usually water, which is going to be used to absorb the energy. And we know the specific heat of the liquid water, and you take a sample at a given temperature and you put it into the calorimeter, and what happens is the water heats up and the sample cools down, and they reach an equilibrium where they have the same temperature. And then you measure the temperature after they've reached equilibrium, and you can use that information to calculate the unknown specific heat for the particular substance. So this is a graph. This would be the temperature of the water, which is lower. This is the temperature of the solid object. So when you put them together, this is hotter than that, and the water heats up and the object cools down, and they reach some final temperature which is the same. And so in this case, because the vessel is insulated, there's no energy transfer from the outside. So all the energy transfer is internal to the calorimeter. The energy gained by the water is the energy lost by the material, the metal or substance. So we can look at the change in energy of the liquid by taking the specific heat of the liquid and the mass of the liquid and the temperature increase of the liquid, and we can look at the change in energy of this object, which is going to be equal to the mass of the object times the specific heat, which we may not know, times the measured temperature difference. And we know these three temperatures, and so basically you have this result. O stands for object, W stands for water, C stands for specific heat, I is the initial temperature of the object and the initial temperature of the water, and then the final temperature is the same for both substances. So a lot of times what you're doing is you're trying to figure out what is this? What is the specific heat of the material? Well, this one here, because you can measure the mass of the material using a balance. We don't know what that is. We can measure the temperatures. We know the mass of the water because we put it in there, and we know the specific heat of water, 4,100 80 something or other. So it's just a matter of doing the algebra to solve for the specific heat. And you could do that. I mean, we could start with this equation, plug all the numbers in and solve for this, or we could just solve for it algebraically. So I think it's not that hard to solve for it algebraically. So if you want to solve for the specific heat of the material, you're just going to have negative the mass of the water times the specific heat of the water times the final temperature of the water minus the initial temperature of the water divided by the mass of the object times the temperature difference of for the object. That's probably one of the easiest algebra things we've done. So let's say we have 2 kilograms of water at 20 degrees C. We drop an unknown object of 3 kilograms and temperature 125 degrees C into the water. After the temperature of the water has stabilized, the temperature is 27 degrees C. What is the specific heat of the unknown object? So all we have to do is plug into the equation, right? That's pretty easy. So we have negative the mass of the water. Mass of the water is 2 kilograms. Specific heat of the water is, let's go back here, it's 4,190. They're joules per kilogram Kelvin. The final temperature is 27. The initial temperature is 20 degrees C. We divide by the mass of the object, which is 3 kilograms. Final temperature 27. Initial temperature 125. Plug that into your calculator. See what we get. You don't have to, because it's a difference in temperature. It seems kind of strange that you don't have to, but it actually does work out okay. But yeah, because anytime you have a temperature difference, you don't have to convert it as long as you're in the right. I mean, this says Kelvin, but because change in C is the same as in Kelvin, because it's different by a constant factor 273, you don't have to worry about it for. Really, the only times you have to worry about it being in Kelvin are calculating the speed of sound, using the ideal gas law. If you did radiation heat transfer, you have to do it in Kelvin. But we're not going to get into that detail. I'm trying to think of other places where you have to have it in Kelvin. Most of the practical situations, you're talking about temperature differences and not absolute temperature. So for example, the expansion of something as you heat it up, it's a temperature difference. If you measure the resistance of some object, it's a function of temperature difference relative to some standard, some reference point.
Makes sense from an energy perspective. Really looking at
Right.
change of energy, not
Yeah. The fun thing, well, let's finish this problem first. So we have negative 2 times 4190 times 27 minus 20 divided by 3 divided by 27 minus 125. And I get let's just write out 199. That's the units are joules per kilogram Kelvin. And it's not surprising. Most metals, I think all metals really, most substances have specific heats less than water. So usually the temperature change for the object is much greater than the temperature change for the Now, if you had where there's a phase change, then it's a little more complicated. If you dropped it in ice, or if you dropped it in a mixture of ice and water, it's not. What you'd have to do is figure out how much energy it takes to get melted first. So if you put the hot object in there, you'd see if it had enough energy as you dropped the object down to the freezing point of the water, if that energy was less than the energy required to melt the ice wouldn't completely melt. Also, it's kind of, if I ask the question, if I mix water, let's say 2 kilograms of water at 70 degrees C with 2 kilograms of water at 30 degrees C, what is the temperature of the mixture? Quick, got to answer in 5 seconds. 4, 3, 2, 1. Well, if you were in a panic mode, you'd probably add them to take the average, right? You'd say, okay, I'm going to average them, right? Because that's all I can do in 5 seconds. And that would have been the right answer, okay? You would have survived if I had a lethal penalty for not answering that question. But because the masses are the same, you've got this, and also this only works if you've got the masses are the same. So when you mix them together, it just comes out to be 50 degrees C.
Yeah, because I was going to say that the change in temperature, they're going to be equal in magnitude,
Right.
but opposite in sign.
Right. Yeah. So since they have the same mass, the temperature's going to have, like you said, opposite signs, equal in amount. To have that happen, it'd have to go to 50 degrees C. I'm assigning Chapter 10 homework. Okay. So that's due next Friday. I'm not sure how many problems are in Chapter 10. I don't think it's that many. It's pretty short. Going to Chapter 11. Actually, that's this Chapter 10. What have we got here? So we talked about, actually, that might have been Chapter 11. Well, I'm still signing Chapter 10. Yeah, I pulled this up. So we talked about temperature. So I'm actually not finished yet. I realized that there was something I hadn't talked about. We talked about temperature. We said two bodies have the same temperature if there's no energy transfer between the two bodies when they're put next to each other. Or you could say two things that are in thermal equilibrium, meaning they have no heat energy transfer, have the same temperature. And that's actually the zeroth law of thermodynamics, that concept of that kind of the definition of temperature is what we call the zeroth law of thermodynamics. And that's because the first law was discovered before the zeroth law. So they came up with 3 laws of thermodynamics, just like there are 3 laws of, actually, is there a third law of thermodynamics? I know there's 2. Anyway, there's at least 2 laws of thermodynamics. So then they came up and they said, oh, we need to have the zeroth law. So that was so let's skip that. We talked about temperature scales, talked about thermal expansion of liquids, of solids more than anything else. That was the thermal expansion coefficient. We didn't talk about the ideal gas law. I couldn't remember whether we talked about the ideal gas law in Chapter 9, but I don't think we did. So one other topic relative to thermal physics is the ideal gas law, which is a special case of what we call an equation of state. What that does, it's an equation. It relates pressure, temperature, and volume and quantity, however you want to define quantity, whether it's moles or mass. There's an ideal gas law that involves mass instead of moles. And I'm sure you saw that in chemistry, PV equals nRT, where R is 8.31 joules per mole Kelvin. And you might be surprised, you're not surprised about the moles because you've got moles here. And it's the number of moles. R is the ideal gas. Here's where you use absolute temperature, ideal gas law. V is the volume, P is the pressure. So let's just define these things, what units you'd use. So P is pressure, and the units are newtons per meter squared, which is called a Pascal. We talked about that in chapter 9. Volume is volume, V is volume, and that has units of meters cubed. And then you have N, which is number of moles. So that's moles. R is called the ideal gas constant. That has units of joules per mole Kelvin. And T is absolute temperature and that's in Kelvin. So even though it's called the ideal gas law, it's actually not as restrictive as you might think. You know, a lot of times we do things in physics and simplify them down, and you think, do they really apply to real situations? So I brought my book in here. I took a class senior year in engineering called gas dynamics. It's not eating too many beans or anything like that. It's and I have this little sticker on the front of my book. I'm proud of the DC-10. So does anybody know what the DC-10 was? Okay, there was an airplane manufacturer called McDonnell Douglas. So it used to be the two main manufacturers of airplanes. It was McDonnell Douglas and Boeing. I mean, Airbus is a big supplier now, and you've got some other smaller ones. But so they used to make, they were, not a half of the airplanes in the United States. Probably about a third of the commercial airplanes in the United States were made by McDonnell Douglas. And anyway, they no longer exist. So one summer I worked, for my master's degree I worked, my major professor did research for McDonnell Douglas. And just before I was ready to go out to California, Long Beach, California for the summer, one of the engines fell off of the DC-10 and crashed and everybody died. And so that was so I don't know how proud I was of the DC-10. I think it wasn't the engine's fault. It was the connection between the engine and the wing that failed. I think they were taken off in Cleveland, and I don't know how far they got off the ground. Let me see if I can find the details of the crash. It should have been around 1979, so we'll see if my memory's good enough. So Google, it's either Chicago or Cleveland. DC-10 crash 1979. There we go. That's the one. Chicago. Okay. So let's read about this. Just on May 25th, 1979, the McDonnell Douglas, so I graduated from college June 1979. So I was going out to Long Beach, California to work for McDonnell Douglas. So just before I went out there, the McDonnell Douglas DC-10 operating this flight crashed just moments after takeoff. 258 passengers and 13 crew on board were killed, along with 2 people on the ground. It is the deadliest aviation accident to occur in the United States. So what happened? The NTSB found as the jet was beginning its takeoff rotation, engine number 1 separated from the left wing, flipping over the top of the wing and landing on the runway. As the engine separated from the aircraft, it severed hydraulic fluid lines that locked the wing's leading edge slats in place and damaged the 3-foot section of the left wing's leading edge. Aerodynamic forces acting on the wing resulted in an uncommanded retraction of the outboard slats. As the jet began to climb, the damaged left wing with no engine produced far less lift than the right wing, and it's going to go anyway. So that is so it was it wasn't the best morale working at McDonnell Douglas that summer. After that, the worst airplane disaster in the United States history. Okay. So anyway, that's my little sticker. So, but if you look at the flow of air around wings or the flow of air in jet engines, it behaves like an ideal gas. So you can use the ideal gas equation. My PhD thesis, which looked at transonic flow, meaning flow between supersonic to subsonic, I used the ideal gas law to relate pressure, temperature, and density in my case. And so with that assumption, you can do a lot of interesting calculations with air in terms of predicting how hot air, so even if you burn fuel in air, it's slightly different than normal air, but it's not enough different that you can't just treat it as an ideal gas. So there's a lot of stuff you can do there. There's also one interesting thing too, related to what we're just talking about. We use this equation: the heat transfer is equal to m, the mass times the specific heat times delta T. For a gas, there are 2 specific heats. So we talked about steam, but there's what's called constant pressure specific heat. And that's called C sub P. And there's constant volume specific heat. And that's called C sub V. And they're not the same. And that's because if you think about a gas, constant pressure specific heat, what you have is you have a gas that's in some kind of a cylinder. Think of it like a combustion, like a car engine. And there's a piston, okay? And the piston has so this is a piston. And the gas is in here. And it's free to move up and down. So by having the piston in there and it lubricated well, as the volume, as you put energy into the gas or take energy away from the gas, the pressure under those conditions stays constant. So if you wanted to look at how much, if I added a certain amount of energy, so I'm going to put some heat in here, and the piston moves up. So if I put heat in here, it's going to get hotter, and it's going to actually cause the piston to go up. So under those circumstances, the heat transfer is going to be equal to the mass times the constant pressure specific heat times the measured change in temperature. The second scenario would be if you had a rigid container, so you don't have a piston, and you've got the gas in there like this, and you put some energy into the gas, and the temperature increases. In this case, the amount of energy put in is going to be the mass times the constant volume specific heat times the change in temperature. So you can't really do that with solids because there's no piston to move. It's fixed. It doesn't change in volume. And in liquids, they're pretty close to the same thing because the volume of a liquid doesn't really change that much with pressure. So it only applies to gases that you have these two different kinds of specific heats. And it turns out that the ratio, if you take the constant pressure specific heat and divide by the constant volume specific heat, as you would name, this is called the ratio of specific heats, okay, because it's the ratio of specific heats. It's very descriptive, nice descriptive. So K is the ratio of specific heats, and if you look in this book on gas dynamics, K turns out to be a really important property for calculating flow of air, and it turns out for air, K is equal to 1.4 approximately. So let me see if I can find some equation that uses, predicts something or another using the ratio of specific heats. Sure, that's with friction. No friction. Frictionless. Yeah, I can't find it. Anyway, actually, I'm gonna read you what you would do in this book, the table of contents. So, basic equations of compressible flow. Wave propagation in compressible media. So they're talking about speed of sound. Isentropic flow of a perfect gas. Isentropic means that there's no change in something called entropy. Okay, so if you have flow in a nozzle where it's insulated nozzle, then you have what's called isentropic flow, and in that case, this K thing turns out to be important. Shock waves, so that's where you go from supersonic flow to subsonic flow. Oblique shock waves. So that's where if you were like flying a supersonic aircraft and out of the leading edge of the airplane, you wouldn't just have a horizontal shock wave. You'd have a shock wave that goes off at angles to the direction of it. So that's pretty cool. I never got to this. Flow with applied electric and magnetic fields. That sounds pretty cool. Imperfect gas effects. So that's when it's not an ideal gas. Rarefied gas dynamics. That's if you're flying out like where there's hardly any air. So if anybody, you guys, that's you guy, Elias. If you're learning about aerospace engineering or aeronautics or something, this is you'll learn as an aerospace engineer. You get to fool with that thing as well. Okay. I think I'll come back to the ideal gas law, but for right now, that's all I'm going to say. We'll do some problems in class. I'm just going to cover some topics today, and then we'll try some problems. So I'm going to go on to, I guess, to chapter 11, but not what that was actually chapter 10. So let me just skip over here. Heat transfer, specific heats. We already talked about that. Calorimeters. Talked about that. There's some more calorimeter stuff. Phase change, latent heat. Covered all that. There's the chart we just dealt with. Now let's look at this. I don't know if you saw anything like this in chemistry or not. This is what's called a phase diagram. So you have a graph of temperature versus pressure, and depending upon where you are with the substance, if you're at high pressure, you might go directly from a gas to you go from a gas to a liquid. here at lower temperatures, you can go from a gas to a solid. So that's sublimation or deposition. If you go from, if you're in this case, if you cool something down, you go across this line. This is where you change from a gas to a liquid. And this line, when you make the phase change, you're going to sit right here until you condense the water, or going the other direction until you boil the water. And then you have, so these just show you the different phases: the solid phase, the gas phase, the liquid phase, and those occur under various combinations of temperature and pressure. So if you're at a high enough temperature, you may never have a solid. So you can think of something like liquid nitrogen. You're never going to have solid nitrogen, even if you go down to, is that right? Am I thinking the wrong way here? Yeah. Well, that's actually not the case. Let me back off on that one. So yeah, if you're at a low enough pressure, you don't have any possibility of having the liquid phase. I guess if you have a high enough pressure, then you can go from solid to liquid to gas. But it's the same thing as an ideal gas. It's like the ideal gas law in some ways. It's relating temperature and pressure. In this case, it's just telling you where you are, which combinations of temperature and pressure put you in the different phases. There's also ones that you would look at for actual properties that are important. Okay, we'll skip over that. Talked about that. Next week we'll do the ice in the cooler experiment, which takes about 2 days. So we'll definitely, there's boiling water, heating steam. Skip over that for a second. Oh, that's really?
So you saw chapter 11, right?
Well, I said chapter 10. It seems like I'm missing something here. Let me look in chapter 12 for a second. I'm going much quicker than I thought I was. Maybe I should slow down a little bit. Where the heck seems like I'm missing something from chapter 11. Just a second. Yeah, because laws of thermodynamics. Okay. Yeah, that must be, well, I'm just going to do it. It's in chapter 12. It's in chapter 11. I don't know why it's not showing up in my notes. So yeah, so it looks like chapter 10 is talking about temperature. It's talking about how temperature affects the length of objects as you change temperature, which we talked about. It's talking about the ideal gas law, which we'll go back and talk about that in more detail another day. Chapter 11 should be talking about how energy relates to temperature change, which relates to the specific heat experiments or examples we did. So we were able to calculate how much energy it takes to take a certain substance. We look mostly at water because that's the most common thing. And then we looked at how calorimeters work. Okay, so the next topic is heat transfer, and it is in chapter 11. I'm not going to assign chapter 11 yet, so I'm going to talk about this topic of heat transfer. So let me draw a picture here. In the simplest case, what you have is you have a solid, and on one side of the solid you have some temperature. We'll call it T sub A. And on the other side of the solid we have some temperature T sub B. And let's say that T sub B is less than T sub A. The question we want to ask in this situation, and also before we do that, there's two other things. There's the thickness of the object, so we'll call that L, and there is some property which we will call, so this is property, it uses the letter K, and it's called the thermal conductivity. And we'll figure out the units here in a second. So the question we're trying to answer is how quickly is energy transferred from side A to side B? Question mark. So one thing you might notice is that when we did the specific heat calculations, we said how much energy, how many joules do I have to put into a substance to raise the temperature a fixed amount? And it depended upon the material. In this case, we're actually not going to heat the material. Well, we're going to assume that we're at some steady state condition. So the temperature here is T sub A and the temperature here is T sub B. And it's going to vary between the two surfaces. And we want to know not how much energy is transferred between A and B, but sides A and B, but how quickly is energy transferred. So it's kind of like how quickly is work done. Energy and work are interchangeable in some sense. They're both joules. So when we talk about heat transfer, we're not talking about, most of the time we're talking about energy transfer rate. So let's just think about the units on this thing. So the units, if we're talking about how quickly energy is transferred, it's going to be joules, not just joules, that's energy, but joules per second. And when we were dealing with work, we called the joule per second a watt. In the case of work, it was work per unit time. Here it's going to be energy per unit time. Okay, and instead of using Q to show the rate of change in the energy or the rate of change in heat transfer, we put a little dot on the top. That's a new terminology. It's kind of like a derivative. So this is actually dq dt. And for some reason, at least when I've taken the class, instead of showing it as Q prime, we show it as Q dot. So this is energy transfer rate, whereas without the dot, it's just energy. And it turns out that rate of energy transfer is equal to K, this thermal conductivity, times the area over which you are, the surface area, not the area here, but the surface area that the two sides of this body are, times T sub A minus T sub B divided by L. So just from a qualitative standpoint, as you increase the temperature difference between the two sides of the object, so here's my object. So it's got a certain thickness, L, and it's got a certain cross-sectional area, A. So if you multiply A times L, you get the volume, but that's irrelevant here because we're not multiplying, we're dividing a bit. So you've got temperature, which, make sure I'm on the right side here. Temperature A here, you've got temperature B here. So it's going to be the thermal conductivity of this book, which is dependent upon what it's made out of, times the area. So the bigger the area, the more energy I could transfer through it. The bigger the house you have, the more energy you can transfer out of it. Then you multiply by the temperature difference. Again, it doesn't matter whether you're in Kelvin or degrees C because it's temperature difference. And divide by L. So the larger L is, the further I have to transfer that energy. Also, the temperature, if I looked at the temperature gradient, which is the rate of change of temperature with respect to X, it's going to be larger for this small book. If I had a big book, I still have the same temperature difference, but I have it over a larger distance. So the delta T over L is actually just what we would call an average temperature gradient So let me just kind of write that out. So if we went over here and we plotted temperature as a function of position, what it would look like is, I'm going to just draw like a graph here. So this is vertical graph is the temperature, and the horizontal is distance. So this would be x, and this would be t. And it turns out that you can show that the relationship is linear, that if this is T sub A and this is T sub B, so put those on your graph, so this is T sub A and this would be T sub B, that it's linear, and that's why we can just simplify it. So the slope of this line is going to be equal to T sub A minus T sub B. Actually, it's that sign might be quite wrong, but we'll figure it out later. And then the distance here is L. So that's basically the slope of this line, temperature versus this distance. And so if you make this thing thicker, you're making the denominator bigger as far as the slope is concerned, and therefore there's not as much gradient in temperature to force the energy through the body. So let's figure out what the units for K are now. So if you so we'll just say so the units for Q dot are joules per second. The units for area are meters squared. The units for length are meters. The units for T sub A minus T sub B are degrees C or Kelvin. So if we put those in, we'll have joules per second is equal to K, the units for K, times meters squared times degrees C divided by meters. So we find out that the units for K are, and this is just meters, not meters squared. So you'll end up with joules per meter degrees C seconds. Okay. So I've got joules per second, divide by, you've got meters, meters squared divided by meters is meters, so you divide by meters, divide by K. So that's the units for K. And K is a material property. So depending upon what you make the object out of, you get a different values of K. So let's find some materials and see what their values for K are. We'll go to Google. Thermal conductivity for, I was going to say stuff. That's probably not a very good. Okay, all kinds of things. So let's look up copper. There's copper. So the thermal conductivity for copper is 401. The thermal conductivity for rubber is, they probably have natural rubber, and there we go, natural rubber, 58. The thermal conductivity for Pyrex glass is 1. So the larger the number, the more easily energy is transferred through that object. Yes?
The rubber is 0.13.
Oh, was it? Yeah, that's... Yeah, intuitively you would expect it to be low. And it turns out that things that are usually electric conductors are also thermal conductors, because the mechanism of transferring the energy is a lot of times the free electrons moving through the substance. And you're right, I should have realized that was wrong when I read it. What did I actually look at?
Rubidium.
Oh, rubidium, yeah, because 50, I was like, that seems awful. I should listen to my subconscious. But it's hard when you're talking, your brain's thinking at the same time. That's why you say things wrong. But let's see. What else is there in here that might be interesting? Silver. So silver is a good electrical conductor, and I don't know whether that's on my list here or not. Silver, yeah, 429. So all the things that are good electric conductors are typically good heat conductors. And that's why things like if you have a computer, a chip, and a lot of times if it's generating enough heat, kind of like your light bulb there, what you do is you want to dissipate the energy that's being generated in the chip. So they'll put a heat sink on there. And what this heat sink, the heat sink does multiple things. It absorbs the energy in the short term, if you want it to, so it'll heat up, but once it heats up, then you want it to pull the energy away from the heat generating object as quickly as possible. So let me just heat sinks for the Raspberry Pi for what do we want to call it? CPU. Okay. Yeah, so there you go. So what you've got is something that looks like this, and it's probably made of aluminum. And what else is it doing? So it's made out of material that has a high thermal conductivity, typically aluminum. And it's lighter, but the main reason why they use aluminum is not because it's light, it's because it has a high thermal conductivity compared to something like iron. What is the thermal conductivity of iron? It's probably going to be reasonable, but it's not going to be. It's 80. So you're 80 versus 400. So it's aluminum has a much higher thermal conductivity. So and then you have these fins, and the basic idea behind the fins is that as the energy is transferred here through conductivity, then you have a lot of surface area. So you're increasing for the heat transfer to the air. You're increasing the area over which you expose that temperature difference between the air and the fin. It's the reason why air-cooled motorcycles have the fins, and is to increase that surface area. The other thing is you put a fan in it. If you blow air over those fins, what you're doing there is you're doing a different kind of heat transfer. Instead of conduction, it's called convection. And by blowing the air over the fins, you're taking the hot air molecules that are right at the fin surface, and you're replacing that with cooler air. And so the temperature difference between the air and the fin is larger than if you didn't have the fan running. That's why you have fans in your light bulb, is to increase. It's not associated with this. It's sort of associated with this part of it, is that instead of having those little hot air molecules hanging around and not helping your heat transfer, you blow air past it and you create increased heat transfer.
That's like the general rule with computers, is you want to be as far away from thermal equilibrium as possible. So you want to keep like a huge difference between your component and the air, because the closer it gets, the like the slower heat transfer.
Yeah, the slower heat transfer, but you don't want it too hot or you're going to burn right. As long as you don't damage the thing. But yeah, the bigger the temperature difference between the component and the air, the more heat transfer rate you have. And you can think, think about computer components. They're running continuously. They're in a steady state condition. So the temperature at every point is the same, but there is a temperature gradient, not with respect to time, but with respect to position. And there are heat transfer problems where there's both time and position, which gets more complicated. In this case, what we're going to look at, so what we're going to do practically speaking, and I guess we have to do it this Wednesday or next Wednesday. You can, if you're calculating the amount of heat that's transferred from your house or from any building, it basically comes down to this equation. So they always tell you to turn the thermostat down to save energy. Well, if this temperature difference is smaller, then you're going to have less energy transfer. They tell you to put more insulation into your walls. Okay, that increases this. That lowers the amount of energy transfer. You can't do much about that. unless you want a smaller house. Okay, smaller house dissipates less energy than a big house. So if you have a big house, then you're going to pay your electric bill, your power bill. And the final thing is K, and K is dependent upon the material. So you can use foam insulation, you can use batt insulation, you can use no insulation. Each one of those has different thermal conductivity characteristics. And so you can take your house and figure all those things out. You know, how many windows you have, how many doors you have, what's the thermal characteristics of each one of those. You know, siding is not just pretty plastic anymore. If you watch Window World, you see that commercial for Window World, and they put insulation on the back of the siding. So they're changing the thermal characteristics. So it's kind of interesting to do that. Since we'll probably do that the last week, not next week, because we don't have it. I don't think you have time to do that. So anyway, yeah, Monday we'll assign chapter 11 because we're actually getting close to finishing it off. Actually, not Monday because we have a test Monday. So I guess I'll do it on Wednesday. That's another reason why we can't do the other thing on Wednesday. We don't have time. Somebody asked me the question, are you going to have to do ray diagrams? And the answer is yes. So ray diagrams are where you draw the lines and they go through the lens and then they go through the focal point. We did that handout in class. So go back and look at the handout. And if you still have problems, you should have on your computer or your jump drive, there are descriptions doing that all over again, so you can review that. So we're not just using the equations, we are doing ray diagrams.